on some questions where we have static rigid bodies, so either a ladder resting against a wall or resting on a peg. So we're still using moments. We've potentially got some friction involved as well. Okay, so putting together a few different things from our mechanics topic. So in this question, we got a uniform rod. So center of mass acts in the middle. Mass 40 kilograms and length 10 meters. Rest with the end A on a rough horizontal ground, and then rest on a smooth peg 8 meters from A. So let's draw ourselves a little diagram. A on the ground, B up here, and C is where the peg is. So let's put in our weight force. We've got 40G. Okay, and the angle is 15 degrees. We're going to have a reaction force at C. So I'll call that C. We will have a reaction force at A. We will have friction at A, pushing this way. If it's in limiting equilibrium, it means it's on the point of slipping. So our friction is going to be the maximum value it can be. So friction will equal mu r. First of all, we want to find the magnitude of the reaction force at C. So if I take moments about A, that will get rid of these unknowns that I don't know yet, the reaction force at A and friction at A, and leave me with just one unknown. Remember, that is perpendicular to this. So I'm going to take moments about A. So my clockwise moments are the weight force times the perpendicular distance. So I need to find this distance here. Remember, it's uniform, so this length is 5 meters. It's going to be 5 cos 15 to get this length. So 40G times 5 cos 15, which I'm just going to write as 200G cos 15. And then my anti-clockwise moments are the reaction force at C times this length. And AC is 8 meters. So this little bit here is 3. So it's just going to be 8 times the reaction force at C. Make those things equal to each other because we're in equilibrium. So our clockwise moments equal our anti-clockwise moments. So 8 times the reaction force at C equals 200G cos 15. So then divide by 8. So we get 200 times 9.8 times cos 15 divided by 8. Which is 240 newtons to 2 sig fix. Then part B, we want to find the coefficient of friction between the rod and the ground. As I said, we are in limiting equilibrium, and that is when friction equals mu r. This is a maximum value. So I want to find the friction, the coefficient of friction here. I need to find the reaction force and the value of friction. So to find the reaction force at A, we can resolve vertically. Now we've just got to be careful with which bits have vertical components, because there is a vertical component to this reaction force at C. This angle here is 15. If I make that a right angle triangle there, the reaction force at C is the hypotenuse. I want the adjacent. So it's going to be the reaction force at A plus the reaction force at C cos 15 to just get the vertical component equals my forces going down 40G. So then the reaction force at A is 40G minus my value of the reaction force at C that I just worked out. We could go back to using the actual one. So let's just write that as 25G cos 15. That's the reaction force at C times cos 15. I'm going to leave it like that for a minute because I'm going to use it again. Now I need to find the friction at A. So I'm now going to resolve horizontally. So all of my forces going to the right, which is the friction, must equal all of my forces to the left, which is the horizontal component of that reaction force at C. So that's going to be RC sine 15. Again, I'm just going to go and use my exact value, 25G cos 15, and now times that by sine 15. So rearrange this so we get mu as the subject. Mu is the friction over the reaction force. So therefore mu is 25G cos 15 sine 15 over 40G minus 25G cos 15 cos 15. Now we can type that into our calculators. We get 0.3748, so 0.375 to 3 significant figures.